Alright, welcome back. So today we're going to discuss a concept known as the mole. The mole is a very important chemistry concept because it allows us to keep track of atoms in chemistry. So today's objective, I'll be able to describe the mole and its importance in chemistry. So first off, to understand what a mole is it's really just a grouping. Most people, when they think of a mole, they're thinking of the fuzzy critter that runs around under the ground or the big hairy thing on Robert De Niro's face. But the fact that in chemistry, the mole is just a group. And we've got other groups that we are probably pretty familiar with. For instance, if you have two pennies, okay, same person might go as far as calling that a pair of pennies. All a pair is a way of taking two things and making them a singular unit. This is a pair. You could then take 6 pairs or 12 things, and one would even go as far as calling that a dozen. So the question of the day is, how many things do you need to have to constitute a mole? Well, we're talking about keeping track of atoms. So we're talking about something much, much, much smaller than pennies. Infinitesimally smaller than pennies. So we would fathom to guess that this number is going to have to be relatively large. So let's talk a little bit about how this number came to be and what it is. So the guy that did most of the original work on this was Avogadro. Avogadro wanted to come up with a good way to keep track of or a good way to count atoms using mass. Mass was something we could easily measure, things in grams, and he wanted to relate it to counts. So let's take a look at an example of an experiment that he didn't do exactly, but it gets the idea across. So we're going to take hydrogen 1. Just a quick review, remembering that the bottom number or the top number is representative of the mass number, and the mass number represents protons plus neutrons. The bottom number is our atomic number, and it's going to represent the number of protons in an atom. So this particular atom is going to have 1 proton because it's got an atomic number of 1, and it's going to have no neutrons because 1 plus something has to equal 1. Well, it's got to be 0, so there's not going to be any neutrons in this atom. Now I'm going to create a model for this, so I'm going to use pennies and dimes. We're going to call protons pennies, and we're going to call neutrons dimes. Sorry, I'm a little off the screen there. And what we're going to say is that each of these has a mass near each other. Protons turn out to be a little bit heavier than neutrons, but we're going to both say that they both approximately weigh 1 atomic mass unit. So in our hydrogen 1 example, we have no neutrons, so we can kind of ignore that for now. We're just going to focus on how many protons there are. And in this case, it's just 1. So this penny basically models a hydrogen 1 atom. We're ignoring electrons at this point. Now, what Avogadro wanted to do was figure out how many of these hydrogen 1 atoms I would need to get the atomic mass unit to be equal to the number of grams. So in this case, our hydrogen atom weighs 1 atomic mass unit. So how many atoms is it going to take to get to 1 gram? So the question is number of pennies to equal 1 gram. That's the question mark. Okay, so imagine taking these guys and stacking them on a scale. Now if you stack just 1 penny on a scale, you're going to get some extremely small number of grams. 1 atom hardly weighs anything. But if I stacked a second one on here, you would expect this number to double. Now remember, we want to know how many we have to stack on here to get this scale to read 1 gram. So it turns out, if I have hydrogen 1, which is what we're modeling, and I want to get to 1 gram because I want the atomic mass units to be equal to the same in grams, I would need 6 million trillion atoms of hydrogen 1. Now, this number is ginormous, so let's get rid of all the zeros, get it in something a little more useful. 6.02 times 10 to the 23rd. This number is now what we now know as Avogadro's number. This is how many AMUs, or protons in this case, would be required to get to 1 gram of a substance. So Avogadro, by coming up with this number, has now set us up to understand not just hydrogen 1, but really any other atom that we could come up with here. Imagine I had carbon 12 instead. Carbon 12 is going to be made of 6 protons and 6 neutrons. 6 plus 6 is 12, and I know there are 6 protons because the atomic number is 6. So if I was looking at this atom, I would expect it to weigh 12 atomic mass units, because it has 6 protons and 6 neutrons, each weighing 1. So the question would be, how many carbon 12 atoms would I need to get to 12 grams? Well, based on the logic we just used above, knowing that a mole of these would weigh 1 gram, and I have 6 of those, I would need 6.02 times 10 to the 23rd carbon 12 atoms to get 12 grams. So what this has done is it has opened up a door. It has linked a count, a number of atoms, to a mass, which is now going to allow us to relate a weight that I can do on a scale to a number of atoms in the number of atoms in that sample. So real quick, let's back up a little bit. Let's just review, make sure we got that all down. We started originally with the idea of just having a pair. A pair would be 2, just 2 things. We also had the idea of a dozen. A dozen would be 12 things. So you gotta make sure 2, 4, 6, 8, 10, 11, and I'll steal this guy, make 12. How many things do you need for a mole? In this, it turns out that you will always need 6.02 times 10 to the 23rd things.